Okay, hello again. Time for some more high-stakes mathematics. Today we are on, still in the number theory section, we are on prime factorization. So, factor 54 into its prime numbers. So I think 54 is 6 times 9, which I think is 2 times 3 times 3 times 3. Right, because 3 times 3 times 3 is 27, and you times it by 2, you get 54. And already in the database, we do have the fundamental theorem of arithmetic, which says that a prime factorization is a sequence of prime exponents, for which only finitely many have non-zero exponents. So basically, you have a sequence of prime numbers, right? So for example, this one is 2 times 3 cubed, right? So the exponent is 3, and then you have 2 times 3 cubed, and 2 and 3 are prime. And this proof shows that there's a one-to-one correlation. So if you can find a prime factorization of something, then that is a unique sequence. That is a unique representation of the number. Okay. So I think if we prove that 2x dot 3 to the power 3, right? 3 to the power 3 is 27. Equals 54. Okay, and we put an and in there. And 2 is prime. And 3 is prime. That will do it. Okay, but I've made some kind of error. So I think those two brackets go with those two brackets. So it's 3 open brackets, there's 4 open brackets, and then 1, 2, there's only 3 closed brackets. Equals 54, maybe it should be here. No. Good start, getting bogged down on brackets. Okay, so let's just see what MNJ2 can do on its own. Wow. Okay. Well, there you go. That's mathematics on easy mode. So it's done quickly. 2 is prime and 3 is prime because they're all in the database. And then 2 times 3 cubed is 54. Wow. Yeah. Where's all this 7 come from? That's so weird. Like 2 times 7 is 14. But what does 3 cubed have to do with that? Oh, 3 cubed is 27? Okay. That is so weird how it's proven that. I have no idea what that has to do with anything. But, not complaining, it has proven it to be definitely true. So, 2 times 3 cubed is 54. So what does it say? Into its prime factors. So the only prime factors are 2 and 3, because 3 comes up. What? Is 54 divisible by 2? Okay, so one city's been destroyed. I don't know why it's not accepting that. I'm pretty sure that is correct. Factor 54 into its prime factors. 2 times 3 cubed. Do you prefer it that way? Okay, so it was the input method that was wrong. Okay, so it wants it in this form. It doesn't just want to know what its prime factors are. It wants it factored that way. Okay, so we destroyed a couple of cities. You know, a couple of the places are in ruins. It's all right. You know, they'll just the survivors can scrabble through the rubble for food. All right, let's see. 7644. Prime factorization of 7644. Is that? It's definitely even. So that's quite helpful. 7644. Okay, 2, 2, 3, 7, 7, 13. Okay, let's try that. So, back to our proof. Let's get rid of all of this. So, what do we want to prove? We want to prove, and I don't know if you can do this all in massive brackets, but we want to prove that 2 squared times 3 times 7 squared times 13. That's quite a lot, so that might cause us some problems. Okay, let's just check I got the brackets right on that. No, it doesn't like that. Because I didn't want to put a load more brackets in for other stuff. 2 squared, so this is times, so I've got 1, 2, 3, 4, 5 open, and then 1, 2, 3 closed. Okay, yeah, so there's no way that's right. You happy with that? Is it that there needs to be a close bracket here? Okay. If I took this out, right, if I took this out, replace it with A, I would have A times 7 squared, A times 7, so close bracket. So all those brackets are involved in this first term. Then I say times 13, and then I'd have a bracket there. Ugh. Come on. Times 13. All right, let's just take this off, right? Okay, why is that not working? A times B. Have I just been really stupid? What's going on? Okay, is it this? Is the existence of this that's causing a problem? Okay, that's definitely right. Like, that's so weird. Okay, new proof. Let's just wonder if I messed it up somehow there. Okay. Let's try A times B. That's weird. All right, 7 times 3 equals 13. Okay. Was that the problem? That I had too much other stuff? 2 squared, 3, 7 squared, 13. Okay, so 2 squared times 3 times 7 squared okay, times 13, put that in here, and then that needs to be closed off. And then, what was it equal to? Equal to 7644. 7644. Okay, it likes that. And then I say, with brackets, and 2 e dot prime and 3 e dot prime and 7 e dot prime and 13. Am I allowed that many ands? Am I allowed that many ands? I don't know if it... Okay, so maybe it needs an opening bracket. Or did I already open it? I can't remember. I'm really having trouble with these brackets, huh? Maybe if I put that in like that. Okay, it likes that for some reason. Okay. So, can you just do a lot of this yourself? It would be really kind of hilarious if it crashed right now. That would be kind of beautiful after taking the whole time to put all that in. Yeah, it does not like that. Okay. I'm going to pause the recording and I'll be back in 1 second. Okay, and we're back. And I decided to change the number a little bit because I was getting a little bit sick of all those brackets and it was getting a bit difficult. So we're going to try 8232 instead and see if that's a little bit easier. So I think 8232 is this. 2 cubed times 3 times 7 cubed. Okay, so let's have 2 cubed in brackets times 3 times, and then we need 7 cubed. Okay, and then that bracket needs to be closed off like this. And then that equals 8232. 8232. Okay, that's at least grammatically correct. And then we also need and 2, oh dear, 2 e dot prime and 3 e dot prime. And are we allowed to do this? Go all this way. 7 e dot prime. Yeah, okay. It seems to like that. Okay, so let's just be kind to it. So if we say 10,000, let's just rip this out and say, okay, let's assume that we've proven this, right? And then 9,000, let's start at the bottom. We'll start at 100. 2 e dot prime, which we have done like a load of times and we know is true. And then exclamation mark 200, 3 e dot prime. And the next one is 300, 7 e dot prime. And they'll all be in the database, I think, pretty simply. And then if we knew all those, that's just going to be some simple logical thing, right? How is that not possibly unifying? Maybe it's because, like, I'm not sure you're allowed 4 things inside an AND bracket. I don't know if that's allowed. So maybe if I closed this there, and I had that as a... Okay, it's happy with that. So it's happy to have, just do the first bit with, it's happy with triple AND brackets, but it's not happy with quadruple AND brackets. Okay, so that's pretty all straightforward. And MMJ2, can you solve this? Oh, but without crashing, please. Oh. So that's kind of ironic that MMJ2, sometimes it freaks out and crashes on you, but sometimes it just is marvelous. So yeah, it's done this whole calculation, 2 cubed times 3 times 7 cubed, and just bashed it out. Just straight up. Look how many steps it's added. That's amazing. I mean, huge praise for everyone who's worked on MMJ2. I mean, that is just incredible to be able to prove all of that automatically and like backfill in all those steps. Incredible. All right. Metamath proof generated. So we are completely sure that this is true. So it's 2 cubed times 3 times 7 cubed. And I'll probably enter it wrong again and we'll lose Johannesburg. But, you know, that's the way it goes sometimes. Times 7 cubed. Are you happy to accept that? 2 cubed times 3 times 7 cubed. Yeah. I'm pretty sure that is right. There we go. Okay, so we had to have a city destroyed from typos again, but we've only had like 3 cities destroyed today. That's pretty cool. That's not a bad outcome. Okay, so that was prime factorization. I think the next thing could be a little bit complicated, which is like divisors. And it's basically saying like, what are all the factors of 42? So you have to kind of put in like, it's not enough just to have 2 factors like 6 times 7. You need to have all the factors and be sure that you've got all of them. And I think proving that you have all of the factors is a little bit complicated because I think we're going to have to firstly show that up to the square root, we've got everything. So it would have to go up to 7. So we say, does it divide by 1, 2, 3, 4, 5, 6, and 7? Check all of those. And then we'd have to have an argument that like, if it doesn't, if we've checked all of those, that's sufficient. That like, if a number is larger than the square root of something, then it will already have been checked. You know, like the 2 factors, one must be smaller and one must be larger than the square root. So if we checked up to the square root, that's enough. But I really don't know how to prove that. And like, I don't know if it's enough. Or another way we could do it is we could prove like if AB equals 42, then both A and B must be smaller than 42 or smaller than equal to 42. So we could just check everything up to 42. But I don't know if having 42 things is that helpful. So it's a bit of an odd one from a metamath perspective, that it's quite difficult to actually sort of prove that you have the full list. Like that's quite an exhaustive search procedure, which is a bit difficult. Greatest common divisor, least common multiple, those are a bit more interesting. And then we have those three are just summary questions that mix up questions from the previous thing. So yeah, we're getting there. And then maybe look at some algebra and stuff later. But okay, that's a problem for next video. Hope you've enjoyed it. Hope you've had a good time. Thanks for watching, and I'll see you next time.